I'm Roger Peppe, and I'm working, same as Daniel Marty, I'm working full-time on the Q project, which, if you haven't heard of Q, is an amazing configuration-oriented language, which, in my opinion, complements Go beautifully. And there are a few of us along today. If you want to speak about Q, come along and find me afterwards. But in this keynote, I'm going to talk about type parameters in Go, which also we know as generics, and how they can fit nicely into Go, in my opinion. In fact, it turns out that type constraints are a big part of that proposal. But in contrast to Andre Eriksson's keynote yesterday, I'm going to say that avoiding the use of constraints is good, actually, and can have unexpected benefits. You'll have to decide which of us is right. And hopefully, you'll come away with some useful, practical techniques that you can apply to any generic code that you write in the future. So what exactly is this new thing, this new thing, feature in the language that we've been given? It's actually the biggest addition to the language ever. The language spec grew by almost a fifth, which is actually pretty good, considering how big a change it is. There are a bunch of new concepts introduced into the language. We've got type parameters, type constraints, type sets, type inference, lots of new stuff. But the core functionality of generics is actually really simple. And I'll just give a brief overview for those of you who haven't looked at generics before of what they look like. So functions can now have type parameters highlighted here. So here we've got a type parameter t, which is constraint. We've defined this generic function here first, and this is the first, the easiest way function I could think of to illustrate generics. So this particular function, it's a bit boring. It's just returning the first item of a slice. So within a generic function, we've got this type parameter, and you can use these type parameters as just regular types. So here we've declared a 0 variable of type t. But we don't know what t is in advance. And so the type parameter is constrained by an interface type, which I'm going to talk quite a bit about that later. And here we actually are calling our first function, and we pass it the type parameter that we're going to instantiate it with. In this case, we're going to instantiate it with an integer. So, in fact, we can use there's a thing called type inference, which we can use to actually remove the need to explicitly pass that type parameter in. But I'm not going to talk any more about that in this talk. Quite useful though. And unlike interface values, part of the point of generic types is that they're identical in shape on the heap and on the stack everywhere to normal types. So here we can pass a regular normal slice of int into our first function, and that's incredibly useful. So types themselves can also have type parameters. So here I've defined a linked list type, which can hold any value of type t. So similar to functions, we can declare the type parameter as part of the type declaration. And anytime we implement a method, we have to declare that type there. And actually, those two names don't have to match, although it's probably a good idea to do so. And as with functions, you mention the name of the type when you instantiate that linked list, or this particular type. And unlike functions, you have to say it. There's no type inference for now. I was saying for now, and I had this marvelous review from Robert Griesmeyer, who said, maybe not for now, it might be a while. So there's some really difficult issues there. So we're going to have to mention you always have to mention the type when you instantiate a linked list, or instantiate a generic type. But having looked briefly at the syntax, let's go back to think about why we actually want generics. And a big part of it is polymorphism. So Wikipedia describes this as the provision of a single interface to entities of different types, or the use of a single symbol to represent multiple different types. And by that metric, actually, we've already got polymorphism in Go. We've got interfaces. We can hide any type underneath the interface hood, and the code using it doesn't know what type's underneath. And sometimes this is known as existential types in other languages. And function values are also polymorphic in that sense. We can hide an arbitrary function with all the types that it uses and pass that around as a value. And reflection isn't actually part of the language as such, but it's a very important part of Go. Reflection is clearly polymorphic in a way that's more dynamic than other forms. Code using reflection can actively inspect types and implement behavior based on what it sees. So what do type parameters give us over and above the previously existing polymorphism? They give us the capability to write type-safe code where we couldn't before. For example, we can write a container type that only allows storage and retrieval of exactly one type of value. And we didn't know that in advance. So for example, we could write a binary tree or that kind of thing, which is incredibly useful. That's probably the main reason for generics. But the trade-off here is that to be efficient, generic code needs to be generated by the compiler, which means that the compiler needs to be able to know all the possible instantiations of each generic function, which in turn implies significant usage restrictions. For example, you can't take the dynamic type of an interface value and call a generic function with that type. Neither can you use reflection to create a new type, because you can create new types with reflect, and use that with generics. So they're quite restrictive, but for all that, they're a very powerful tool. Now, many of us, myself included, we worry about the potential impact of generics on Go. And I saw that box yesterday. There are a lot of people putting those tokens in the no box. And Go has historically valued simplicity, readable code very highly. Not all languages with generics have those same values. We could end up in a situation where we find almost every Go program an impenetrable mass of generic code. I really hope it doesn't turn out that way. So we actually have generics now. They're in the language. We're going to build that type-safe container. How should we use them? How can we choose to demonstrate good taste and together create an ecosystem that feels simple and Go-like? We'd like to be able to understand what makes for nice generic code and how generic code and APIs can fit well alongside the existing Go ecosystem without corrupting it. And in this talk, I'll try and show a few simple techniques that potentially could help. So when we looked at the example code earlier, it looked pretty simple. So where did all that complexity in the specification come from? Turns out that a lot of the complexity comes from the notion of type sets, which are actually an extremely elegant solution to the problem of how we can allow generic code to operate directly on built-in types. One of the big sticking points of earlier generics proposals was their lack of ability to do this. Ian Lance Taylor, in particular, wrote this: I claim that, other than type-safe data structures, the number one generic function that people want to write is min, or max. I don't think we can plausibly add a generic system to Go that doesn't permit writing a min function. So that was his bar for the new generics in Go. So here's what a min function looks like. you can see we've defined an ordered interface, which allows it mentions every possible type in Go which has an ordering associated with it. So strings you can compare, like for ordering integers, and all the other sizes of int. I haven't mentioned them all here because there are quite a few. And here we've constrained our type, the type parameter to min, by this ordered interface. And because every type in that interface allows the less than operator, we can use it in the code just like that. So that's very simple. It looks like it you might expect. So although typesets are adding much of the complexity, existing interface types that you're already familiar with can also be used as constraints on types in type parameters. They allow us to, that means that you can invoke methods directly on generic values, just as you can invoke methods on interface values. Now, I've been following along in the generics channel in the Go for Slack for ages now. And almost all the questions seem to be about constraints in one form or another. People are asking, how can I constrain this type parameter to do this particular thing? And they're definitely one of the harder things in the language to grok. And although constraints are really useful in some places, and we just saw a nice example of that, I'm going to argue here that they're actually not necessary in many cases, and in fact, that you'll tend to get further without them than you can with them. So, okay, here's a concrete example. I'm sure that most of us has used strings.join before. Raise your hand if you have used strings.join. Keep your hand up and lower your hand if you've never been a bit frustrated that you can't pass something else to strings.join, like something that implements stringer. So like a slice of durations. I don't see too many. So quite a few hands still up, because I certainly have. You want to pass this slice, and you end up having to make a copy of the slice or implement the join functionality yourself, and it's a bit frustrating. Because commonly you have these values that know how to convert themselves to string, but then you can't actually pass it to this usual function that joins up strings. So we can actually use type parameters to solve that. This join implementation will work on any slice of a type that implements stringer. For example, it works just fine with this slice of time.durations. You couldn't pass that as a slice of string because they're not strings. You couldn't pass that to a slice of stringer because it's not a slice of stringer. It's a slice of time.duration. So notice how we're actually constraining that T with an existing interface type that's actually been there all along. So that means that we can invoke those string methods on those elements of the type. So that actually worked great when we had a slice of something that actually implemented stringer. But what if you've got a slice of some built-in type, like int? It's not going to work. What if we don't actually want to use the string method of the type? For example, maybe we've got a slice of times, and we want to format them as RFC 3339 rather than the default output, because time.string is not very useful. It's great for debugging, but it's not hugely useful. So there's another possibility. It turns out we can implement almost exactly the same function, but instead of constraining the type parameter, we can use a function value to define the mapping from type to string. So here you can see we've got, instead of using, you can see the two different examples. Here's the original one with stringer, and here's the new one with, so we're constraining by any, so it's any type, we're unconstrained, and instead we've got this toString function which takes anything of type T and returns a string, and then instead of calling the string function directly on the element, we call the toString method to convert to string. Now, how does this actually turn out in practice? Because it's no good if this unconstrained thing is a bit awkward to use. But in my opinion, it turns out pretty neatly. So for the stringer case, you can actually use a method expression to get a function that converts from time.duration to string. For integers and strings, for other built-in types, we probably have built-in functions that already exist that also implement this function. We can, if we want RFC 3339, we could pass a closure rather than use string. And we can even implement our original constrained join function in terms of this new unconstrained function, which shows that the unconstrained thing is actually strictly more general because we can implement it in terms of this unconstrained function. So what can we take away from this? So you're using existing Go features, closures, method expressions, things that were defined in Go well before generics, alongside the new type parameters. And the unconstrained version is actually strictly more powerful and useful than the constrained version. Here's another somewhat more involved example, which is taken directly from the type parameters proposal. It was taken from both proposals. There was at least two sequences of proposals, and this example was in both of them. So here we're talking about a directed graph, and it's defined in terms of two types. A node, which knows what edges it's connected to. So it's got a method called edges, which returns a slice of edges. And we've got an edge, which knows what nodes it's connecting. So this is, as like a directed graph is, it's kind of recursive. So here we've got the constraints, and they're mutually recursive constraints, which is kind of funky. So we've got the node, which is constrained by edge, and we've got edge, which is constrained by node. And this is kind of, funky, and it turns out that anytime we have a function that operates in terms of this, we have to mention those constraints every time, right? So we have to write out those constraints in full, and that graph type there, I think was there in the proposal just because it would be a pain if we had to mention those constraints for every algorithm we want to implement on the graph. So that, because we've got that method there, we don't actually have to mention the constraints in the method. But I think that's just to ease the pain, right? it's not a great thing. But as with the join example, it's a bit too constrained because there are actually many possible representations for a graph, and not all of them map nicely to the API that we just saw. For example, what if my representation doesn't have a node type that encapsulates all its edges? Writing code that layers on top and implements the required constraints is bulky, awkward, and potentially inefficient. Let's try unconstraining this API. Here's the result. So instead of using a function value, as we did with our join example, we're using an interface. So rather than having constraints that constrain the type parameters themselves, we accept a generic interface that implements operations in terms of those generic values. Because there are no constraints, it's not such a burden to mention those type parameters. And the previously mutually recursive relationship between edges and nodes is now neatly encapsulated in this graph interface type. It's 2 lines rather than 10 or so. So here's one possible implementation of a graph type. It's about the simplest representation I could come up with. So here we're representing a node as just an integer, simple integer, and we can see that node 0 there is connected to 1 and 2, node 1 is connected to 5, node 2 is connected to 0, 4, and 5, and we've got a graphical representation of it just there. The natural representation for a node here is an integer, and with the other representation, even if we did use a typed integer, which would enable us to implement an edges method on it, it wouldn't have enough information to be able to return the connected nodes, because it's just an integer after all. The connected edges, anyway. So here's our actual implementation of that. It's fairly straightforward. The node type is int, so we're just using int here. And our edge type is we're using just an array of two integers, of two nodes, the from and the to. So you can observe that because we're using an interface value as opposed to constraints directly on the type parameters, we always have access to the core graph object so that we can use that to fulfill our contract. So for example, if we wanted an auxiliary field that allowed us to return style information for some edges, that would be easy to do, for example. We could change the edge type to include that information. So, and as with the previous join example, we can actually easily define the original constrained version in terms of this new unconstrained implementation. So here's the proof of that. Because in the constrained implementation, node and edge have all the information we need, this graph implementation is just an empty struct that implements the required behavior by invoking methods on the values directly. And as with join, it actually takes very little code to implement this constrained implementation in terms of the unconstrained implementation. So the unconstrained is kind of strictly more general. So what can we take away from this? We've used an existing Go feature, an interface, alongside generics. So we've made a generic implementation more general without actually compromising at all on the amount of complexity in the code. And think about how powerful this technique is for a moment. That generic interface has defined in one convenient place a kind of algebra that relates otherwise unrelated types to one another. We've used a graph algorithm for illustration here, but it could also have been arithmetic, for example, writing an algorithm that works on both built-in number types and big int, etc., or actually any number of other possible applications. Those types themselves aren't actually aware that they're part of the implementation. And the type operators themselves always have access to the interface value with any other state that might be needed. For example, as we saw just a moment ago, those types might be short integer references to some internal data structure. So I've shown, I hope, how removing constraints can make your code more general. But there's still one constraint still left, which is the types themselves. If we have a generic type as part of a struct, unless we know the type parameters statically, we need to declare them on the container type, which is fine in principle, but when the new type has no methods at all that actually use the type parameter, it feels like a bit of a burden to have to parameterize the type everywhere. So, for example, in this imaginary package, we're wrapping a graph type with another type that knows how to render a graph into mermaid format, because mermaid's cool. We've discovered about it. I discovered about it recently with GitHub's support. It's quite cool. So and in this case, even though the only method we wish to implement, Marshall mermaid, like Marshall JSON, but for mermaids, doesn't use the type parameters at all, we still need to declare them on the mermaid graph type because they're used in this field. Even though that field isn't exported, the outer struct needs to declare the same type parameters. So here's an alternative version of the API, which looks almost the same, except that the type we're returning doesn't actually have any type parameters. How can we do this? So this particular trick is known in the Swift world as type erasure, and it's actually a super useful technique. I've seen it come up in a bunch of different use cases. And following the common theme of this talk, we've combined type parameters with a feature already present in Go, interfaces. But this time, instead of using a generic interface, we're defining a normal, regular interface, which declares the methods we need and is implemented by this generic graph impl type. So that's what we were seeing. That's similar to what we were seeing before, but now we're wrapping it inside this graph interface type. So the outer level graph type embeds this new interface, which kind of erases the generic type. So which means that graph doesn't need to have those type parameters anymore. We can also use a function value to accomplish a similar thing. And there's a subtle detail here. We could just return the interface type. We could return so we could export that Marshall Mermaid interface type. But in general, in Go, you don't want to return interface types because that constrains you, or that means that you can't add new methods without potentially breaking your clients, without potentially breaking the API. So in this case, we're defining this struct type, this graph type, and putting the interface in it, which means that you have the advantage that you have a static type, but you've also got this erased, you can erase the type parameters. And there are actually a bunch of other uses for this use case. You could, for example, putting multiple instances of a generic type inside a slice, storing generic values inside global variables. For example, you might have a global cache indexed by type, that kind of thing. So, to conclude, use less constraints, frees up your code to do more things. I hope I've shown you in general that you can write useful code without using type constraints, that it's actually more useful than similar code that's constrained. Constraints definitely have their place, as with min, but I hope you'll consider the unconstrained approach too. And Go values composability and orthogonality, and type parameters fit very nicely into that framework. We can compose generics with all our existing Go features. There are sure to be many more interesting and useful ways to combine type parameters with those features. And when type parameters are getting in your way, you can use interfaces and closures to stop this virus, resulting in package APIs that look very similar to early pre-generics Go, but leverage all the power of generics under the hood. So thank you very much. If you'd like to talk to me about generics or Q later, please come and find me. Thank you very much.